Good morning, students. In this video, first I will discuss about limitation of octet rule. In the last video, I have discussed up to Lewis dot structure of covalent compounds. Okay, so today's first topic is limitation of octet rule. Limitation of octet rule. First is incomplete octet of the central atom. In some chemical compounds, the central atom the central atom has less than 8 electrons, that is incomplete octet. For example, in lithium chloride, lithium has 2 electrons in its valence shell. In beryllium hydride, beryllium has total 4 electrons in its valence shell. In BCl3, in BF3, in all this compound, boron has total 6 electron in its valence shell. So these are incomplete octet, although these compounds are exist. Okay, so these are incomplete octet. In some chemical compounds, the central atom has incomplete octet. Second limitation is, say, expanded octet, that is more than in many chemical compounds there are more than 8 electron in the valence shell. Okay, in many chemical compounds there are more than 8 electron in the valence shell of the central atom. For example, in SF6, in SF6 sulfur hexafluoride, sulfur atom has total, in SF6 sulfur atom has total 12 electron in its valence shell, although this compound exists. In PF5 phosphorus has total in PF5 phosphorus has total 10 electron in its valence shell. In IF7 iodine heptafluoride, iodine has total 14 electron in its valence shell. So in some chemical compounds octet is expanded, more than 8 electrons are present. Third limitation is odd electron molecules or odd electron chemical bond. We know that generally for a chemical bond at least 2 electrons are required, but there are in certain chemical compounds like in NO, like in NO2, like in oxygen molecules, there are 3 electrons bond exist. 3 electron bonds, that is odd electron bond, odd number of electrons. Okay, so in example is in nitric oxide, in NO 3 electrons bond are there, in NO2. Okay, so these are exceptional case from octet rule. Okay, and other drawbacks of octet theory also given. Some noble gases also combine with oxygen and fluorine to form a number of compounds like XCF2, XCOF2. We generally know that noble gases do not form any chemical compounds. But in some cases, some noble gases like xenon, in few cases krypton can also form compound with fluorine, oxygen. Okay, and this octet theory does not account for the shape of molecule. It does not give any idea about the energy of the molecule and their relative stability. Okay, so these are some drawback of octet rule. Now see bond parameter. What is bond parameter? Some parameters or physical parameters are required to describe a chemical bond, a covalent bond completely. So there are mainly 3 types of bond parameters are there. Bond length, in simple word, bond length means it is the equilibrium distance between the center of two bonded atom. Okay, it is the equilibrium distance between the center of two bonded atom, and it is expressed in terms of angstrom unit. Okay, so simply the bond length means bond length, this distance Ra plus Rb. Okay, distance between two atom. Second bond parameter is bond angle. Bond angle, what is bond angle? It is defined as the angle between the lines representing the orbital containing the bonding electrons. For example, in water, you can see in water the hydrogen oxygen hydrogen bond angle is 104 degree. Huh? So this is the bond angle, the angle between the lines representing the orbitals containing bonding electron. In methane, each hydrogen carbon hydrogen bond angle is 109 degree 20 minutes. Okay, so this is bond angle. Okay, so to describe the bond, you have to mention the bond angle also. Okay, bond length, bond angle, and the third bond parameter is bond enthalpy or bond dissociation energy. Okay, it is defined as the amount of energy required to break 1 mole of bonds of a particular type to separate them into gaseous atom. It is defined as the amount of energy required to break 1 mole of bonds of a particular type to separate them into gaseous atom. Bond enthalpy also known as bond dissociation enthalpy, and it is expressed in kilojoule per mole unit. Okay, and greater the bond enthalpy or bond dissociation energy, stronger is the bond. Remember this. Higher is the greater the bond enthalpy or bond dissociation energy, stronger is the bond. Okay, for example, bond dissociation energy of hydrogen between two hydrogen atom in hydrogen molecule is 435.8 kilojoule per mole. Bond dissociation energy of some bonds here given, it is hydrogen bond dissociation energy is 435.8. Chlorine single bond dissociation energy is 239 and 239 kilojoule per mole. These values are not required. Okay, so see this. Remember that carbon single bond, the bond dissociation energy between bond dissociation energy of carbon single bond is less than carbon double bond, which is less than carbon triple bond, because in carbon triple bond triple covalent in carbon triple covalent bond is present, which is stronger than double covalent bond, which is stronger than single covalent bond. So bond dissociation energy of carbon triple bond is more than carbon double bond, in which is more than carbon single bond. Similarly, bond dissociation energy of nitrogen double bond, which is more than nitrogen bond dissociation energy of nitrogen triple bond, which is more than bond dissociation energy of nitrogen double bond, which is more than nitrogen single bond. Okay, and last bond parameter, which is bond order. It is bond order means types of bond present between two atoms, single bond or double bond or covalent triple bond. Okay, so in a covalent bond, the bond order is given by the number of bonds between two atoms in a molecule. For example, in hydrogen molecule, there is a single covalent bond between two hydrogen atoms, so bond order is 1. Okay, in oxygen molecule, a double covalent bond is present in oxygen molecule between two oxygen atoms, so bond order is 2 in oxygen molecule. In nitrogen molecule, bond order is 3, because a triple covalent bond is present between two nitrogen atoms. Okay, so higher the bond order, greater will be the bond strength, better will be the bond stability, higher will be the bond dissociation energy. Okay, so these are the bond parameter. Now see an important term, resonance and resonance structure. What is resonance and what are resonance structure? There are many molecules, many chemical compounds, mainly covalent compounds. There are many covalent compounds whose behavior cannot be explained by a single Lewis structure. Okay, so For this type of molecule, you have to draw more than one Lewis structure, and this phenomena is known as resonance. More than one structure of a single molecule to explain all the properties of the molecule. Okay, for example, here two structure of ozone O3 molecules, two structure of O3 molecule is given. This is a structure 1 and this is structure 2. In first structure of ozone, you can see you can see this is the single bond and this is the double bond. There is a single bond, one single, it is actually coordinate bond, and one is double covalent bond. In structure 2, you can see this double covalent bond is converted into single coordinate bond, and that single bond is converted into double bond. Okay, so here actually delocalization of pi bond takes place. Pi bond means in a double bond, one bond is single sigma bond, another bond is pi bond. Okay, in a double bond, one bond is sigma bond, another is bond is pi bond. Okay, and due to resonance, delocalization of the pi bond take place between oxygen. Okay, so due to resonance, all these two bonds are equivalent. Okay, and due to resonance, their bond length also become equal, and both the oxygen bond length become 128 picometer. Okay, so this one structure 1 and structure 2 are known as resonance structure or canonical form of ozone, canonical form, and this phenomena is known as resonance. And the average structure of these two molecules, that is this structure, is known as resonance hybrid of ozone. Okay, due to resonance, all the oxygen bond length in ozone molecule become equal, and the value is 128 picometer. Okay, so thus according to the concept of resonance, whenever a single Lewis structure cannot explain all the properties of the molecule, the molecule is then supposed to have many structure with similar energy. And during writing the resonance structure or canonical structure of a compound, position of atom, bonding and non-bonding pair of electrons are taken as the canonical structure of the hybrid, which describe the molecule accurately. Okay, so during writing the structure of resonance, the position of each atom must be same. There is no change in position of each atom. Okay, and total number of covalent bond will be equal. Total number of electron in all the structure must be equal. These are some conditions for formation of resonance. Okay, so here resonance structure of different molecules are given, like carbon dioxide, carbon monoxide, nitrous oxide, nitrous acid, hydrozoic acid, nitric acid. Okay, you have to practice all this resonance structure of all these molecule. First one is carbon dioxide. Due to resonance, this structure, this bond becomes triple bond, and this bond becomes single covalent bond. Okay, and this oxygen becomes O minus by gaining electron, and this oxygen, the right side oxygen, after using this lone pair, this oxygen form a triple bond between carbon and oxygen, you can see. Okay, alternatively you can also write this carbon oxygen bond as a triple bond, and this is as a single bond. Okay, so different structure you have to draw, different structure of a single molecule. In carbon monoxide has three type of structure. In one structure you can see a double covalent bond. In structure 2, a single covalent bond between oxygen and carbon, and in above carbon it is positive charge, and above nitrogen oxygen it is negative charge, you have to write. In third structure, carbon oxygen is triple covalent bond, and on negative charge on carbon and positive charge on oxygen. A structure of nitrous oxide. N2O it is given. Hmm. 3 structure of N2O is given. A structure of resonance structure of nitric acid HNO3. First you have to know what is the Lewis dot structure. Then after delocalizing the pi electron, this pi electron, this bond will be double bond and this bond will be single bond. Okay, so 2 structure of HNO3 is given here. So all this structure you have to practice, resonance structure of different covalent molecules. Now next topic is bond polarity. What is bond polarity? You know, covalent compounds are two type. One is polar covalent compounds, another is non-polar covalent compounds. Non-polar covalent compounds or non-polar covalent bonds are formed between two similar atoms. Same type of atoms when combined, when they form chemical compound covalent bonds, then the covalent bond is non-polar covalent bond. Okay, but if the covalent bond is found between two different electronegative atoms, uh, atoms having different electronegativity, then the shared electron pair between two atoms get displaced towards the highly electronegative atom, and therefore the highly electronegative atom acquires a negative charge and the less electropositive atom acquires a positive charge. For example, in HCl, in hydrogen chloride, in hydrogen chloride, electronegativity of chlorine is more, so chlorine will attract this covalently electron bonding electron pair toward itself in a larger extent. So chlorine acquires a partial negative charge and hydrogen acquire a partial positive charge, because electronegativity of chlorine is much more than hydrogen. So chlorine will attract the electron pair of the covalent bond. Similarly in HF is also polar covalent bond due to difference in electronegativity between hydrogen and fluorine. Okay, negative charge, partial negative charge above fluorine and partial positive charge above hydrogen. Okay, so these are polar covalent bond, and polar covalent bonds are formed between two different electronegative atom. Now see next topic, important topic, it is dipole moment. And what is the use of dipole moment? It is used to measure the polarity of a covalent bond. Okay, I have told that some covalent compounds or covalent bonds are polar in nature, which are formed by between two different electronegative atom, and the polarity of a covalent bond is measured in terms of dipole moment. Okay, dipole moment is a physical quantity, it is a vector quantity, and according to by definition uh, dipole moment is defined as the product of magnitude of charge, product of magnitude of charge product of magnitude of positive or negative charge and the distance between the charges. It is defined as the product of magnitude of positive and negative charge and the distance between the charges. Huh. So mathematically, dipole moment, which is represented by mu, the symbol mu, dipole moment means mu. Using this symbol, generally dipole moment is represented. So dipole moment is equal to charge into distance between two atoms. Okay, and SI unit of dipole moment is, it is a charge, that is coulomb meter. One in CGS unit is ESU centimeter, and one more unit is dBi. dBi is the unit of dipole moment. 1 dBi is equal to, the relation is given, you can see. So dipole moment is the measure of polarity of a covalent bond, and it is indicated by giving a arrow. Using this arrow you have to show the electron displacement. For example, in ammonia nitrogen has 3 covalent bond, okay, and 1 lone pair, and lone pair movement is in this direction always, and the hydrogen nitrogen bond movement of all the 3 hydrogen nitrogen bond movement is towards nitrogen, because nitrogen is more electronegative than hydrogen. You have to show the bond movement of each bond by giving an arrow like this. Okay, so ammonia is a polar covalent bond. If dipole moment of a molecule is 0, then the molecule is non-polar. For example, in CO2, in CO2, the bond moment of two CO bond is opposite to each other. So net dipole moment mu is equal to 0 for carbon dioxide. So CO2 is a non-polar molecule. Non-polar molecule, CO2. Okay, and if the dipole moment is not 0, then the molecule is a polar molecule. Remember this. For example, in water, hydrogen, oxygen, hydrogen. Okay, so each bond movement of each oxygen hydrogen bond is in this direction, hydrogen to oxygen. huh? And the lone pair movement of in water, oxygen has two lone pair, so lone pair movement always out in the outside direction. Okay, so net resultant dipole moment of this water molecule is positive. Okay, so oxygen positive, that is not is equal to 0, greater than 0. So water is a polar molecule. Okay, it has some dipole moment. Okay. Carbon dioxide is non-polar molecule. Okay, so application of dipole moment, using this term you can tell which molecules are polar, which are not, which are non-polar. Okay, so application of dipole moment. So dipole moment is equal to, mathematically, dipole moment mu is equal to charge into distance, E into d. E means charge, or you can also write q into d. It is expressed in d by unit. Okay, and the term dipole moment is related to covalent molecules. Now see, application of dipole moment, it is used for determining the polarity of molecules. If dipole moment is 0, then the molecule is non-polar. If dipole moment is not is equal to 0, then the molecule is polar. Okay, it is also used in finding the shape of molecules. For example, molecules with 0 dipole moment will be linear molecule, and those molecules which have unsymmetrical shape will have bent or angular shape, and they have positive dipole moment. Okay, and in calculating the percentage of ionic character in polar covalent bond, dipole moment term is used. Okay, so in your book, there are many examples of calculation of dipole moment of different compounds are given. You have to practice all this structure. Okay, dipole moment of BF3, you can see dipole moment of BF3, VF3. First you have to draw the structure. First you have to draw the structure of BF3. So BF3, in BF3 there are total 3 BF bond, and the bond moment of each BF bond is in such a way that is bond polarity resultant of two bond movement will cancel the bond moment of third BF bond. As a result, the total dipole moment of BF3 molecule is 0. So BF3 is a non-polar molecule. Okay, many examples are given, many structure. With the drawing you have to explain dipole moment. It polar molecule or non-polar molecule? For that you have to find out the dipole moment of the molecules. Okay, next day I'll discuss about valence shell electron pair repulsion theory. Thank you, students.